When we're working with derivatives and integrals, we can also work with inverse trig functions. Now, working with inverse trig functions in general is fun, but when we get to add derivatives of integration, it becomes even more so. Now, I assume all of you have a strong background in trigonometry, and because of trigonometry, you also know all the information you need to know about inverse trig, but just in case, and because I enjoy doing it, I'm going to review some inverse trig information. So to get started, when we're talking about an inverse trig function, you might see something like y equals inverse sine of x. Now, another way that we could write this is y equal arc sine of x. These are interchangeable notations. One thing I want you to understand, though, the inverse sine of x does not equal 1 over sine of x. Okay, now when we talk about an inverse function, we have all sorts of characteristics we learned in algebra. For instance, the domain and the range swap, they mirror around the line x equal y. So these are all these interesting things about inverse trig functions, but this is the most important relationship. This notation up here does not mean to flip the sign, it means inverse sine. Okay, so because we started talking about inverse sine, we'll do that first. So for the inverse sine of x, let's go ahead and start with the sine of x. Now the sine of x is a familiar graph to us. It starts at the origin, looks something like this, and of course these go on forever in either direction. It crosses at 0 and pi, it peaks at pi and negative pi over 2. So these are some nice little characteristics about this graph. Neat little graph. Now, when we start talking about the sine function and we start talking about inverses, that's where we run into trouble, because in order for an inverse to exist, it has to pass the horizontal line test, and you can see pretty clearly that this graph does not pass the horizontal line test anywhere. Well, it will pass it if we restrict the domain. Okay, so let's talk about the restricted sign. Now, when we talk about the restricted sign, what we're getting after is where can I restrict the domain and range to so an inverse does exist. Now, there's all sorts of different regions. We could go negative pi over 2 to positive pi over 2. That should be a 3 pi over 2. I'll fix that in a second. But that's kind of not very near the origin, so that kind of seems inconvenient. Let me fix this one right here. It should have been a 3 pi over 2. And we could also restrict it, let's say, between negative pi over 2 and 0. So there's all sorts of different regions we could restrict it to. And what we have all agreed to is to restrict it between negative and positive pi over 2. So the restricted domain is negative pi over 2 to positive pi over 2. Now the range, the restricted range then along with that, goes from negative 1 to 1. Now this is also the range of the standard sine curve that's not restricted, but it's also the restricted sine range as well. Now when we talk about the inverse sine then, we can talk about its domain and range as well. Now remember, for a function and its inverse, the domain and the range swap. So the domain down here will be negative 1 to 1 because it came from the range above, and the range will be negative to positive pi over 2 bracketed, points inclusive. Now you're going to want to know these restrictions because they'll come in handy a lot. Let's go ahead and look at the same for cosine. So let's look at the cosine graph. Cosine graph starts up here at 1. Looks something like this. And you might say, well, let's restrict it from negative to positive pi over 2, just like we did with our other graph. But you'll see right away that that doesn't work very well because it doesn't pass the inverse sine test there either. So let me fill in these values. So if we restricted this between negative pi over 2 and pi over 2, just like we did with the sine curve, you can see it won't pass the horizontal line test, so it doesn't have an inverse over that region. So what we're going to do is we're going to restrict the cosine function between 0 and pi, and then you can see that it does have an inverse because it passes the horizontal line test on that interval. So on the inverse sine, inverse cosine, let's go ahead and first of all look at the restricted cosine. if we look at the domain and the range, the domain is restricted between 0 and pi, points inclusive. These are bracketed. And of course the range goes from -1 to 1 again. Now for the inverse cosine, and this is not the graph of the inverse cosine. This is just, I'm building the idea of the inverse off of our standard graph. The domain and the range swap. So the domain will be -1 to 1, and the range will be 0 to pi. Now we'll talk about the meaning of the restricted cosine and the restricted sine as it applies to the inverse sine and cosine a little bit further on. But for now we want to just set up these characteristics of these graphs and these restrictions for these graphs so they're easy to work with. Next, let's go ahead and look at the tangent graph. So here I have y equal tangent of x. Now the tangent graph is an interesting graph. Of course, tangent is sine over cosine. So I'm going to have problems wherever the cosine equals 0. So whenever I start this graph, what I do is I look at the cosine first to find out where my asymptotes are. So if we look at a sketch of this cosine curve, what we can do then is kind of build the tangent curve off of it. So I'll do the cosine curve just very, very lightly here. And everywhere it crosses, there's basically going to be a vertical asymptote for the tangent graph. So all of these are vertical asymptotes for the tangent graph. And again, this is built off the cosine curve. Now the tangent of 0 is 0, so that puts me right here at the origin. The first quadrant tangent's positive, so I know I'm up in this region. So this is what the tangent graph looks like. Now one thing I didn't do is plug in these values. So this value is pi over 2, so this is x equal pi over 2. This is pi, x equal 3 pi over 2. Over here, this is x is equal to negative pi over 2. This is negative pi, and this is x equal negative 3 pi over 2. Okay, so if we look at this graph, it does not pass the horizontal line test either, so an inverse doesn't exist. However, we need to restrict the domain, and then it will exist. Let's get that part of the graph back. So if we want that part of the graph to exist, where do we restrict it from? And as it turns out, we restrict it similar to the sine graph. So let's go look at restricted tangent. So we're going to restrict our domain between negative and positive pi over 2, but I have to have parentheses here and not brackets because I have vertical asymptotes at negative and positive pi over 2. And my range goes from negative to positive infinity. So basically I'm restricting it right here along the quadrants that are closest to the origin. Now if we talk about the inverse tangent then, the domain and the range swap. So the domain is negative to positive infinity, and the range is negative to positive pi over 2, parentheses, not brackets. Now those are the ones that you'll use the most often. Inverse sine, inverse cosine, inverse tangent, but I'll look at the other ones as well very quickly. Now these other ones build off the same exact idea. You would draw the curve that's related to it, you'd look at the asymptotes, you'd restrict it. So let's just go ahead and look at cosecant to get started with. For the cosecant graph, we would restrict the domain. So for the restricted cosecant graph, my domain would go from negative pi over 2 bracketed to 0, union 0 to pi over 2 bracketed. Now the range is pretty interesting. It goes from negative infinity up to negative 1 bracketed, union positive 1 off to infinity. So that's the restricted cosecant graph. Now if I talk about the inverse cosecant, these would swap. So my domain here would be negative infinity to negative 1 bracketed, union 1 to infinity. And the range would be negative pi over 2 to 0, union 0 to pi over 2. Now these can be bracketed because they do not have asymptotic lines at negative and positive pi over 2. Let's go ahead and do the same thing for secant. So for secant, we need to restrict before an inverse can exist. And the way that we'll restrict that domain then for secant is going to be 0 to pi over 2, bracketed 0 to pi over 2. Pi over 2 is a parenthesis because there's a vertical asymptote there. Then it picks up at pi over 2 and heads off toward pi, which is bracketed as well. The range goes from negative infinity to negative 1, bracketed, union, 1 to infinity. And then when I talk about the inverse secant over here, the domain and the range swap. That's one of the characteristics of an inverse function. So the domain and the range swap. Now, like I said, the ones that are used most commonly are the inverse sine, inverse cosine, inverse tangent, but you really should be aware of all of these. So these are good things to have on your note card for the exam. The last one that we'll look at is the inverse cotangent. So we'll look at cotangent. We'll restrict the cotangent. So the domain and the range. So for the domain, for the cotangent, we'll go 0 to pi, parentheses, not brackets. And then our range is negative to positive infinity. Then so for our inverse cotangent, we'll have our domain and the range, and remember they swap. So the domain would be negative to positive infinity, and the range would be from 0 to pi. So these are all characteristics that will be important to know, and you can create the restrictions by looking at the graphs and keeping near the origin, and then come up with, of course, the domain and the range of your inverse trig functions. Now you say, this is wonderful. What do I do with all these inverse trig functions? Well, this is still review over trig, but let's go ahead and answer a few questions. Now this will also get you used to how you can show your work on your written assignment and on the exam. So let's look at y equal the inverse sine of negative 1/2. Now technically there's a lot of different solutions for this unless you remember the restriction. So when you show your work for this, you need to write out what it's asking you, and what it's asking you for is an angle. So this is your work for this. What angle in the interval, and this is my restriction, negative to positive pi over 2, has a sine of negative 1/2. So if we think about this, I'm restricting myself from negative pi over 2 to positive pi over 2. So I'm somewhere in here. Because the sign is negative, I know I have to be down in this region. So basically, what angle in this region has a sine of negative 1/2? Now we have to be careful when we write this. You know, when you think about negative 1/2, it's going to be a negative pi over 6 that would fulfill this. And this would be your correct answer. However, if somebody comes over here and says, oh, that's 7, 8, 9 pi over 6, 10, 11 pi over 6. 11 pi over 6 is not correct. That is an angle that gets you to the same location but with a different amount of rotation. So you have to make sure that you use this value of negative pi over 6 and not the 11 pi over 6. So again, this is the work that I would expect to see when you're solving these. Let's look at quite a few more. Inverse cosine of negative 1/2. So this means what angle, and we have to remember the restriction now, 0 to pi has a cosine of negative 1/2. Now I'm not going to draw these out every time, but to get us started, inverse cosine, what we're talking about here then, is an angle in the first or second quadrant. So what angle has a cosine of negative 1/2? Well, it has to be over here in this quadrant. And so when we're talking about a negative cosine, that puts us in the second quadrant. And we need a cosine of negative 1/2. Well, that looks like to me that if we have our angles memorized, this would be 2 pi over 3. So what angle has a cosine of negative 1/2? That would be 2 pi over 3. Okay, so again, you can check these pretty straightforward. And when you're working with these, it's really important that you keep in mind those restrictions, because without those restrictions, you cannot answer these consistently and correctly. So it's important that you know about the unit circle, because without the knowledge of the unit circle, these problems would be very, very difficult. I also noticed when I was checking some of these on Mathway and Wolfram Alpha, just some other ones so I could get a little idea of what kind of solutions they give you. Mathway did not look at the restriction correctly. It looked at, up in here, it looked at 11 pi over 6 for the solution on this one, I believe, or something similar. So you have to be careful when you're using your calculators and outside resources. They might not match, I guess, some of these solutions. Okay, so again, inverse trig function means what angle? So that's the first thing that you should think about and write. The restriction here is from negative to positive pi over 2. So what angle in the interval from negative to positive pi over 2 has a sine of 0? And that one's pretty easy, that's 0. And again, that just comes from knowledge of the unit circle. Let's look at a few more of these. Let's look at a tangent. Let's look at y equal the inverse tangent of -1. This means what angle, and again, anytime you see an inverse trig function, you need to think what angle. And in this case, our restriction is negative to positive pi over 2, but these are not brackets, they're parentheses because I have asymptotic lines here. So what angle in the interval negative to positive pi over 2 has a tangent of -1? And that is going to be negative pi over 4. That's the angle negative pi over 4. So again, when you're working with these, make sure that you keep in mind the unit circle. If you're not good with the unit circle, make sure you have that on your notes for the test, because it will come in handy. Now another neat thing you can do with the inverse trig functions, and eventually we're going to use these to evaluate definite integrals, but we're just kind of practicing with these right now, is you can embed them. So when you have an embedded trig and an inverse trig function, you start on the inside. So this means what angle in the interval negative to positive pi over 2, and again, this is the work I expect to see here for these, has a sine of negative square root of 3 over 2. So that's the question here. Now, once I find this answer, then I plug it into the sine. So my answer here, what angle in the interval from negative to positive pi over 2 has a sine of negative square root of 3 over 2? That's going to be negative pi over 3. So negative pi over 3 comes in here. And so this says, what is the sine of negative pi over 3? And it is negative square root of 3 over 2. So for here, it almost looks like the inverse sine and the sine undo each other, and I just get the argument back. Now this is true sometimes, but not all the time. Let's look at a few other options here. Let's look at the inverse cosine of the cosine of 5 pi over 4. So you'd think again that these would cancel, but they not necessarily do. So let's look on the inside first. So this is not a big question with this one. This just says what's the cosine of 5 pi over 4. 5 pi over 4 is in the third quadrant, so the cosine is going to be a negative, and again, your knowledge of the unit circle tells you that's negative square root of 2 over 2. Now this piece, this is a question, and this is the work you show. What angle in the interval 0 to pi has a cosine of negative square root of 2 over 2? That's the question. And if you think about that, that has to be in the second quadrant, because the cosine is negative in the second quadrant, and it has to be a pi over 4 multiple, so here we would get 3 pi over 4 for our solution. So you can see the inverse cosine and the cosine just don't undo each other. You have to consider the restrictions on those inverse trig functions. Let's look at a few more of those. If I can get this to advance, there we go. Let's look at the inverse sine of the tangent of pi over 2. So we'd start on the inside. The tangent of pi over 2, okay, if you don't have this memorized, remember that's sine of pi over 2 over the cosine of pi over 2. The sine of pi over 2 is 1, cosine of pi over 2 is 0. This is undefined. Okay, so what I'm basically looking at here then is the inverse sine of undefined. So this doesn't even make sense here, so this is no solution. So you have to be careful again when you're popping these back and forth and in and out of the inverse trig functions and trig functions that you're not skipping a step or missing something about restrictions. So this one we'd start with the cosine of pi. The cosine of pi is -1. There's nothing to show you there. It's just basic knowledge of the unit circle. Now this one we do want to talk about the restriction. So the work I would show is what angle in the interval from negative to positive pi over 2, parentheses here, not brackets, has a tangent of -1. And now this is knowledge of your unit circle. That's negative pi over 4. Okay, so again, knowing your unit circle is going to be very, very important. Now these inverse trigs are going to come up again toward the end of this section when we start using integration, and then we start evaluating inverse trig functions. The next thing we're going to look at are derivatives of trig functions. I should say of inverse trig functions, because we already know our derivatives of the other trig functions. Now these are definitely ones that you'll want to know. So these are important. I would say to put these on your formula sheet for your test. The derivative with respect to x of the inverse sine of u is going to be u prime over the square root of 1 minus u squared. The derivative with respect to x of the inverse cosine of u, the only difference here is a negative sign, is a negative u prime over 1 minus u squared. So I'm pairing these up because the only difference is a negative. Okay, let's look at the derivative with respect to x. Let's do inverse tangent here. It's going to be u prime over 1 plus u squared. The derivative with respect to x of the inverse cotangent, let's use u here. U is some algebraic expression typically. It doesn't have to be, but it's some expression involving x. And in order to find this, we need a negative u prime. We need to take the derivative of the argument over 1 plus the argument squared. Last one we'll look at here is secant, and then it's negative. The derivative of the inverse secant of u. This one's a little bit trickier. This is going to be u prime over the absolute value of u square root u squared minus 1. And then of course the negative of that would be the inverse cosecant. Let me make that inverse cosecant. So it's negative u prime, absolute value of u, root u squared minus 1. Now a couple things to keep in mind. Any of these radicals have to be positive. So when I talk about 1 minus u squared, that tells me that 1 minus u squared has to be greater than or equal to 0. Actually, it has to just be greater than 0. It's in the denominator, so it can't be equal to 0. Same with u squared minus 1, root u squared minus 1 has to be greater than 0. And there's no way that 1 plus u squared could be equal to 0 or could be negative, because I'm taking something squared as positive plus a positive is another positive. So there's some restrictions that you need to keep in mind, and of course these have more to do with the u value in here than anything, but just make sure that you're keeping these real. These have to be real numbers. Now these are not very tricky to work with because I just follow the form. So again, in order to be successful with these, you have to make sure you follow the formulas. So let's go ahead and look at the derivative with respect to x of the cosine of the inverse sine of 3w. Now we can't start off on the inside here and it says what angle has a sine of 3w. I'm not sure about that. I guess I could go through and develop a right triangle and try and kind of work it from there, would be one option, or I can just go right after my derivative. Now remember, the derivative of the cosine of u, this is u, this is the argument of my trig function. So this is going to be equal to the negative sine of u times the derivative of u. So let's think about that. Negative sine of u, and u in this case is the inverse sine of 3w. Now I need the derivative with respect to x, or w in this case I guess, since we have w's here, of 3w. Okay, so that's kind of what we're looking at here so far, is when we're looking at these derivatives. Now, I think we're missing one thing here. The derivative of the cosine of u is negative sine of u prime. So we know what u is, but my u prime is incorrect here. I actually needed the entire u was the derivative with respect to u of the inverse sine of 3w. Okay, so this part stays the same. Okay, now this piece, the derivative of the inverse sine of 3w, that's one of our forms. That's going to be the derivative of 3w, so I'm going to call that 3w prime over root 1 minus the quantity 3w squared. So simplifying, I have negative sine inverse sine of 3w. Now the derivative of 3w is just going to be 3, and here I'll have 1 minus 9w squared. Now there's little simplifications that we can do here. Now remember when I talked about the inverse sine and the sine sometimes don't cancel each other out depending on these angles? Well, when we have an expression that's not just a standard angle that we're looking at, what I do is I can just look at this and say, okay, these do cancel each other because we don't have knowledge of what the angles are. So we could just call this negative 3w times 3 over the square root of 1 minus 9w squared. And this simplifies to negative 9w over root 1 minus 9w squared. So there's our derivative of that function that we started with. So again, knowing your basic derivatives is important as well. Let's look at another one. This will involve the product rule, because of course you can use the product rule, chain rule, quotient rule, all those good things. Let's look at 11x squared inverse sine. Let's do 3x here. So this is going to be the product rule. So my product rule would say my first function times the derivative of my second function plus my second function times the derivative of my first function. Okay, so I haven't taken the derivative yet. The only thing I've done is kind of set up and showed my work. Okay, so the derivative of the inverse sine of 3x, that's the derivative of 3x is 3 over root 1 minus 3x quantity squared is 9x squared plus the inverse sine of 3x, and the derivative of 11x squared is going to be 22x. So here's my derivative. I guess I can simplify it a little bit. Most of these don't simplify much. 11 times 3 is 33x squared over root 1 minus 9x squared. Now remember what this is. I'm going to put the 22x out front. And the reason I'm going to pull that out front is so we don't get it confused with the argument of this trig function. Remember, this still means the same thing. This is the slope of the tangent line at any point along the curve. If this is the position function, this is the velocity. So I should still be able to go through and evaluate these functions too. So again, this is an example of the product rule. And you could have the quotient rule and many others as well. Another set that you're going to want to have for your formula sheet are inverse trig integrals. Now these are a little bit different than the book gives you. I'm giving you kind of a generic u value instead of x's here. If you have an integral of the form 1 over the square root of a squared minus u squared du, that integrates into inverse sine of u over a. And I'm kind of a stickler for this. I should have mentioned it before to make sure that you're aware of it. But always put parentheses around the arguments of your trig functions, because otherwise, just like in the example we have up here, if I didn't have parentheses here, it would combine with this 22x and that would be incorrect. So I'll try to mention this more often, but always put parentheses around the arguments of your trig function. This is an indefinite integral, so we have our plus c. Let's go ahead and look at 1 over a squared plus u squared. So if I have an integral that fits this form, this integrates into 1 over a inverse tangent of u over a. And again, always put parentheses around the arguments of your trig function. Now this next one, u squared minus a squared du, this is going to fit inverse secant. So this is 1 over u inverse secant, but this is absolute value of u over a. And again, very important that you have parentheses around the arguments of your trig functions. So you'll need to know those three forms, and we're going to use those three forms in a couple of examples. Let's look at the integral of 8 over the square root of 16 minus x squared dx. So the way I'd usually start these is by rewriting these. I'd pull any constants out, and then I think of this is not a u substitution because there's no x up here to use a u as x squared, du as 2x, something like that. So down here this would be a 4 squared minus x squared. So my a is equal to 4 and my u is equal to x. Okay, so if I make these substitutions, this fits that form perfectly. So I'd have a squared minus u squared, and if u is x, du is dx. So this fits perfect. Now if we come up and look, 1 over a squared minus u squared is inverse sine. So I drag that 8 along, and this is the inverse sine of u over a. But we know what u is. U is x over 4 plus c. Now this is an indefinite integral, but this would be the perfect chance to evaluate an inverse trig function as well if this was a definite integral. Let's look at another one. Let's look at the integral of 1 over x square root x squared minus 441 dx. This fits an inverse secant pretty clear, but let's go ahead and rewrite it so we can see it. So this is x quantity squared. Square root of 441 is 21. So then we see here that a is 21, u is x, and then of course du would be dx. So subbing back in to see if it fits its form, this would be 1 over u root u squared minus a squared du. And this should fit 1 over a inverse secant absolute value of u over a. So this is 1 over 21 inverse secant, whoops, absolute value though, of u over a. So that's x over 21. Now here I don't need parentheses around the argument of my trig function because I have absolute values. But if up in this problem you've got to have those parentheses to define what your argument is, because it's very easily confused with other things running around in the equation, and we don't want to get those messed up. Let's try a few more of these. Let's do 25x squared plus 36 dx. Now, first of all, you'd always try a u substitution. So if we let u equal 25x squared plus 36, we would need a 50x, and you can see I can get a 50 but not an x. So that tells me I need to look at this form. So rewriting this, this is 5x quantity squared plus 6 quantity squared dx. A is 6, u is 5x, du is 5 dx. So I have all this stuff going around. So I multiply by a 5 on the inside, compensate with a 1/5 on the outside, and I can pull the 7 out too, and I have 7/5 integral 1 over u squared plus a squared du. So this is going to be 7/5, and then this integrates into inverse tangent, which is 1 over a inverse tangent of u over a. Now again, you always have to have the parentheses around the arguments of your trig functions. Simplify, this is 7 over 30 inverse tangent 5x over 6 plus your constant of integration because this is an indefinite integral. Let's go ahead and look at a couple definite integrals. These are the fun ones. I love inverse trig. I love trig. Okay. Let's look at this integral. So we're going to integrate from 0 to 7/8, and we'll have 1 over the square root of 49 minus 16x squared dx. So this is a definite integral, but all we really need to worry about right now is the integration portion. So let's go ahead and rewrite this. Drag along our constants of integration, or sorry, drag along my limits of integration. This would be 7 squared minus 4x quantity squared dx. So a would be 7, u would be 4x, du would be 4 dx. So I'd multiply by a 4 on the inside, compensate with a 1/4 on the outside, and then when I rewrite my integral, This is going to be 1 over the square root of a squared minus u squared du. Now notice I have dropped my limits of integration, and the reason I've dropped them because here they're in terms of x. So this is in terms of x. Now this is in terms of u, so having a 0 and a 7/8 here wouldn't make sense. If I want to change my limits of integration, I can. So I either need to drop them or change them, but I can't leave them the same when I'm using u substitution. It's something to keep in mind and look for. This fits the form of an inverse sine. So this is the inverse sine, and again, parentheses around the arguments of your trig function, u over a. But no plus c this time. Now because I've converted back into my values for x, I can evaluate this from 0 to 7/8. So this is going to be the inverse sine of 4/7 times 7/8, because I'm plugging in my upper minus my lower, inverse sine of 4/7 times 0. And again, always put parentheses around the arguments of your trig functions. 7's cancel, 4 goes into 8 twice. Here I'll get a 0, so I'm left with 1/4 inverse sine of 1/2. Always put parentheses around the arguments of your trig functions. Inverse sine of 0. So I have two questions to answer here, and again, these are the ones that you show your work on. This is an easy one to miss, and I don't want anybody to miss these, so that's why I insist that you show your work on these. This means what angle in the interval from negative to positive pi over 2 has a sine of 1/2? And the answer to that is pi over 6. This one means what angle in the interval between negative pi over 2 and pi over 2 has a sine of 0? And the answer to that one is 0. Oops, I forgot part of this one over here. This is negative to positive pi over 2. So plugging these back in, I end up with 1/4. The inverse sine of 1/2 was pi over 6. The inverse sine of 0 was 0, so I get pi over 24. Now if you want to think about it, this is the area underneath that curve from 0 to 7/8, so you could look at a curve sketch of this if you wanted to kind of clarify what this is. Also, if this was your acceleration function up here, your original, this would be velocity when you integrated it. Let's look at one last one. These are fun. This one, really important that you know your unit circle. Let's look at the integral of 1 over 4 plus 3x squared dx. Now, again, I'm just going to do a little side note here. Typically, when I would see a problem like this, I'd say, oh, let's try u substitution. Du then would be 6x dx, and then there's no way for me to get this x here, so u sub doesn't work. So that's when I start to recognize my inverse trig forms. But you should always try u sub first because it could work. So we'll rewrite this and see if we can make it fit a form. So this would be 2 squared plus, now this one's interesting. This has to be something squared. Now before we had things like 16 or 9, something like that. Here was a 16 and a 49. Those are perfect squares. 441. But 3 is not a perfect square. So I need to think about what is the square root of 3? And that's the square root of 3x. Notice the x is not under the radical. So when I write this, I have an a value of 2. My u is the square root of 3x. Du then is root 3 dx. So using compensation, I'd multiply by root 3 on the inside, compensate with the 1 over root 3 on the outside. And this would look like 1 over a squared plus u squared du, which 1 over root 3 integrates into 1 over a inverse tangent of u over a. Always put parentheses around the arguments of your trig functions. So this is 1 over root 3, and then a in this case is 2. 1 over 2 inverse tangent u root 3 x over 2. And then this is not a plus c. I'll evaluate this as soon as I simplify it. So I get 1 over 2 root 3 inverse tangent of square root of 3x all over 2. Evaluated from, I forgot to put in limits of integration on this one. Let's put them in. These will be good ones. Let's put in, well, we want something that'll work slick here. So let's try negative 2 root 3 over 3 all the way up to negative 2/3. And I'll show you what this graph looks like too when we get a little further on. So negative 2 root 3 over 3 and a negative 2/3. So this 1 over 2 root 3 I can pull out front because it's a constant. And then I have this inverse tangent of the square root of 3 over 2. And then my upper I'd plug in a negative 2/3. And then I'd subtract out my lower, inverse tangent, square root of 3 over 2. And then my lower would be a negative 2 root 3 over 3. Okay, there's a lot going on here. So I have that 1 over 2 root 3 out front. And this first one simplifies to the inverse tangent of the 2's cancel, and I'm left with negative root 3 over 3. Ah, that's an interesting one. Minus the inverse tangent. Now here the 2's cancel, and I'm left with root 3 times root 3 is 3. The 3's cancel, and I'm left with just that negative 1. So there's two questions being asked here. What angle, and again you need to show this, what angle in the interval from negative to positive pi over 2, points not inclusive, has a tangent of negative square root of 3 over 3. Now this one's not, I don't know this one off the top of my head as easily as I do my other ones, so I have to think about this one. Remember sine over cosine, so I'm looking for sine of pi over 6, cosine pi over 6. Yeah, that would work here. So pi over 6 would work, but because it's negative, this is a negative pi over 6. Okay, this one, what angle, and again, this is how you show your work for these. What happens is a lot of people respond with not an angle but a value here, so that's why it's so important to write out what angle in the interval from negative to positive pi over 2, points not inclusive, that means we're using parentheses, has a tangent of negative 1. And that's just basic knowledge of your unit circle. That's negative pi over 4. So these are the ones that we'd plug in here. So I have 1 over 2 root 3, negative pi over 6 minus, upper minus lower, and negative pi over 4. So continuing to simplify here, I get 1 over 2 root 3, negative pi over 6 plus pi over 4. Finding that common denominator. So I'd negative 4 pi plus 6 pi over 24. So 6 pi minus 4 pi is 2 pi over 24. The 2's would cancel, and I'm left with pi over 24 square roots of 3. Now remember, this is area under that curve. Now, what does this curve look like? It's kind of an interesting curve. The original problem was the integral of 1 over 4 plus 3x squared. Let me try that again, 4 plus 3x squared dx. And this went from negative, what did we decide, 2 root 3 over 3 to a negative 2/3. This graph is very interesting. First of all, it has horizontal asymptotes right through here, because if you took the limit of this as it approached infinity, you'd get 0. If I plug a 0 in here, I get a 1/4 back out. So we're going to call this 1. This would be a half, this would be a 4th. So this curve comes up here and down again like this. And so I'm looking for the region between negative 2 root 3 over 3 and negative 2/3. So the region I'm looking for is somewhere right in here. You don't have to know the curve sketch, but sometimes it's interesting. As usual, if you have questions, please let me know. It's very important that you get some of these onto your note card for the exam, because you can memorize these, but they're handy just to have on a note card as well. You need to know your unit circle. It's just vitally important. You also have to be able to show your work. And this is the kind of work that you need to show up here for your inverse trig function. So make sure you're aware of what question you're asking and where the restriction is. If you have questions, please let me know. As a quick text or a picture in a text works really well. You also have Pearson Connect, and you can also contact me if you'd like to set up some online office hours. Good luck, and please let me know if you have questions. This will be a fun assignment.